Dear students, continuing with our lecture series on named reactions, this is our eighth lecture, and today in this lecture we will discuss what is Negishi coupling and what is its mechanism and its applications. The basically Negishi reaction was studied by E. Negishi in 1976, and what he did is he studied the reactions of aryl halides, alkynyl halides, alkynyl halides, or acyl halides with organozinc compounds in presence of either palladium ligands or nickel ligands to give us products with the formation of new carbon-carbon. So that is why this reaction is very important, because here in addition to palladium catalyst we can use nickel catalyst also, and this palladium or nickel catalyzed stereoselective cross coupling of organozinc compounds with different kinds of organic halides ranging from aryl halides to alkynyl halides. Alkynyl halides means halides containing carbon-carbon double bond, alkynyl halides containing carbon-carbon triple bond. So all these categories of uh, organic halides, when they are reacted with organozinc compounds in presence of either palladium or nickel catalyst, they undergo stereoselective cross-coupling reaction for the formation of a new carbon-carbon bond. And such a coupling is known as Negishi cross-coupling or simply Negishi reaction. The mechanism as far as nickel catalyzed reaction or palladium catalyzed reactions is slightly different from each other. For example, in case of nickel catalyzed reactions, in the first uh, step, the nickel 2 compounds, they react with the organozinc compound with the elimination of zinc halides. They nickel compounds, they are converted into organonickel compounds, and these organonickel compounds, they react with different types of alkyl halides or organic halides, which may range from saturated to unsaturated halides. These two, they undergo oxidative addition, and the organohalide adds to the nickel complex, and this nickel to organic halide complex then again reacts with organozinc compound and undergo transmetallation reaction, wherein the X part of this nickel 2 complex is removed, and the R part or organo part of the zinc halide gets attached to the nickel complex, and we will get these types of complexes with the elimination of zinc halides. Then these nickel 2 organo nickel 2 complexes, they coordinate uh, with the aryl halides or acyl halides or alkynyl halides or alkynyl halides, and a coordination bond is formed between the organohalide and the nickel 2 complex formed by transmetallation. And then this may undergo oxidative addition, and a circle of reaction is again undertaken with the elimination of the product through reductive elimination. So R1 from the alkyl halide and R from this nickel, they form a new bond to give us the product, whereas the rest of the molecule again undergoes oxidative addition, and the new reaction again starts. So this is how the nickel catalyzed reactions, they gave us products with new carbon-carbon bond formation. Similarly, in case of palladium catalyzed reactions, the palladium zero catalysts, they react with the alkyl halides, and we will get uh, the oxidative addition reaction wherein the alkyl halides adds to the palladium complex to convert this from zero oxidation state to the 2 oxidation state. And this 2 oxidation state palladium complex then reacts with organozinc compound and undergoes transmetallation reaction to give us this palladium 2 organo complexes, and these palladium 2 organo complexes, they undergo reductive elimination to form a new carbon-carbon bond between this R group and R1 group to give us the stereoselective products through palladium catalyzed reactions. So this is how we can differentiate between the mechanism involved in nickel catalyzed reaction and palladium catalyzed reactions. And then the applications of Negishi reaction is that we can have very common examples addition of heterocyclic aromatic compounds containing halides to bromopyridine reacts with pyridyl organozinc compound, and under Negishi conditions, either in presence of nickel complexes or palladium complexes, they will undergo formation of a new carbon-carbon bond at this carbon and this carbon. Br from here and Zn X from here. So zinc halides, they are removed and a new carbon-carbon bond is formed. So we will get 2,2- bipyridines as the product of Negishi coupling in these types of reactions. Similarly, biphenyls can be synthesized if we react orthotolyl zinc chloride. This is orthotolyl zinc chloride with orthoiodotoluene, and again I from here, zinc chloride from here, and there will be a formation of carbon-carbon bond at this place, and we will get substituted biphenyls as the product under Negishi conditions. Then this Negishi coupling has also been employed for the synthesis of hexaferrocenyl benzene, where R is ferrocene over here. So when hexa iodobenzene is reacted with diferrocenyl zinc. Here R is ferrocenyl group. So diferrocenyl zinc, when 6 molecules of this diferrocenyl zinc, they are reacted with hexaiodobenzene in the presence of palladium catalyst, tris dibenzyl benzalidine acetone dipalladium complex in THFS solvent. So at 68 degrees centigrade and in 63 hours, we will get to 4% of this type of product which is formed. So hexa ferrocenyl benzene is formed in 4% of it. And this is again very important reaction of Negishi. Then some industrial applications of Negishi coupling is this Negishi coupling is not frequently employed in industry in comparison to Suzuki reaction or Heck reaction. Basically because the organozinc reagent which we use for Negishi coupling, they are very sensitive to air and water, and because of that their stability is need to be uh, considered before having industrial application, whereas the catalysts used in Suzuki reaction or Heck reaction, they are much more stable than the organozinc reagents. So that is why Suzuki reaction and Heck reaction, they find more applications in industry as compared to Negishi. However, Novartis, they have employed Negishi coupling in manufacture of a phosphodiesterase type 4D inhibitor, a compound PD478, which was a lead drug for the treatment of asthma. Then this synthesis of benzodioxazole, which is a synthetic intermediate for the synthesis of some drug, is synthesized through Negishi coupling of this type of aryl bromide, substituted aryl bromide. When this is reacted with hexylithium in presence of THF pentane and zinc chloride, this is converted into this organozinc compound. In presence of hexylithium plus first this will be converted into lithium complex, and then that lithium complex will react with zinc chloride, and lithium chloride will be eliminated, and we will get this type of organozinc compound. And then this organozinc compound reacts with this benzodioxazoyl bromide and zinc chloride from here, bromide from here. They are eliminated, and there will be formation of carbon-carbon bond at this carbon and this carbon. And we will get this type of benzodioxazole derivative in 73% yield in uh, 4.5 kg scale in the industry. So this is also a very important reaction under Negishi conditions. Then Negishi reaction is also used in the total synthesis of many natural products. And one such reaction is the synthesis of stemoimide. This is the stemoimide, which is a natural product found in the root extracts of Stimona tuberosa, and this is a folk Chinese medicine or Japanese medicine which is used to treat respiratory disorders. So because of its use in Japan and China, this synthesis of this natural product is very important. And in addition to treatment for respiratory disorder, this has also been used as an antithelmintic activity. Here what happens is one of the steps in the synthesis of this stemoimide is this reaction where beta gamma unsaturated ester, this zinc bromoethyl acetate, is reacted with an intermediate diene like this. So this iodine reacts with this ester, and we will get this type of beta gamma unsaturated ester as the product in 78% heat. And again reaction take place in presence of Negishi conditions, and this after few steps can be converted into stimulate. In fact, after this we need to have 12 more steps for overall production of this compound in 20%. Then another natural product, pumiliotoxin B, which is a toxic alkaloid isolated from Dendrobatus plumea, which is a poison frog of Panama. This toxic alkaloid, this shows a modulatory effect on voltage dependent sodium channels. So therefore this is having cardiotonic and myotonic activity present in this alkaloid, pumiliotoxin B. So that is why the synthesis of this alkaloid is very important because of this cardiotonic and myotonic activity possessed by this alkaloid. And this can be synthesized through some of the steps involving Negishi coupling. And here what happens is when this type of organozinc compound, uh, this is zinc alkylidine indozylidine, this is reacted with e-vinyl iodide of this type, where these hydroxyl groups they have been protected by this group secondary isobutyl. When this is reacted, this organozinc compound is reacted with this e-vinyl iodide. So under palladium catalyst, in the presence of palladium catalyst, what will happen? So there will be a formation of a new carbon-carbon bond. This carbon from the organozinc compound and this carbon from the vinyl iodide. So zinc iodide from here, tertiary butyl zinc iodide is removed and this will form a carbon-carbon bond to give us this type of product. And this, when this is deprotected, this will lead to the formation of pumiliotoxin B, which is a toxic alkali having cardiotonic and myotonic activity. So again, this is a very important reaction which takes place under Negishi conditions. Then another natural product which is also very important and possessing bipyridine system is cerulomycin C. This cerulomycin C can also be synthesized through Negishi coupling. So when 2-pyridyl lithium, 2-lithiopyridine is reacted with this type of aryl halide, 6-bromo pyridine derivative. These are coupled under Negishi conditions in presence of zinc chloride and palladium compound. They will give us this type of product in 80% yield, where uh, this carbon from the 2-lithiopyridine and this carbon from the aryl halide will undergo formation of a new carbon-carbon bond to give us this product. And this on further reactions can be, this part of the molecule on further reaction can be converted into this type of oxime, which is a cerulomycin C, a natural product containing 2,2-bipyridine system. And this is again a very important biologically active compound. Then another important natural product synthesis is the stereoselective synthesis of amphidinolite A, which is having this structure, and this is prepared from the reaction of an homoallylic alkyl zinc reagent, this one, which when this is coupled with this type of e-vinyl iodide under Negishi conditions, this is converted into this type of intermediate, uh, 1,5 diene intermediate, where this is 7,8 double bond, which is formed by formation of a carbon-carbon bond between this carbon and this carbon of the e-vinyl iodide and this carbon of the homoallylic alkyl zinc compound. And through different steps this can be converted into this type of amphidinolite natural product, which shows C7C8 double bond stereoselectivity. This is C7C8 bond. So this has been displaced a bit. Uh, and these types of compounds, they are biologically very active and used as drugs in some diseases. These are the references which has been used for preparing this reaction, this lecture. Thank you very much.